Good day, everyone, and welcome to where we are putting together solutions for students in the area of primary math. Today, we will be looking at the secondary entrance assessment, or better known as the SEA, and it will be looking at 2025. Because this topic is so big, this whole idea of the subject of math, for students who are getting problems, it is better if they take one section at a time. So today we'll be looking at section 1. Don't forget to like the video and add any comments down below so we will be able to create any more videos for those who need help. Don't forget that we have similar channels for Form 5 CXC Mathematics and for additional mathematics, which you can find in the description down below. So let's now go to our paper, where we're going to look at the distribution of marks. And when we look at the distribution of marks, remember that there are 4 strands in mathematics. The first strand is number, and it almost takes up half of the entire of math. Now there are 20 questions in section 1. So number takes up half of those from numbers 1 to 10. The next major strand in the SCA paper is measurement. And that is assessed in the next 4 questions, 11 to 14. And then it moves on to the third strand, geometry, where 3 questions are assessed, numbers 15, 16, and 17. And to complete this section 1, the 4th strand is statistics. And the last 3 questions, 18, 19, and 20, covers off this section. By students being able to go through this and understand the key concepts that's happening, that is being assessed, it will help them build a good foundation to handle any question. So let's go. Let's start by looking at number 1. In this question, pretty much a place value sort of question, write the numeral represented below. So they gave this diagram, and that's all that was given. So I would like to bring up a little place value chart because you're accustomed doing that with teachers. So on the extreme right will be ones, and the next column will be tens, and the third column will be hundreds. And there are different ways to do this. Some teachers teach thousands next and so forth. I've found that students who are getting problems, it's easier for them to recognize the pattern that if we have ones and tens and hundreds, that pattern is repeated again. So it's ones in the 4th column, tens in the 5th column, hundreds in the next column. And if it had to go on, it would repeat with ones and tens and hundreds. And the first 3 of them will be from the family or the period called ones. And the next 3 numbers are from the family of thousands. And if we had another set coming, it would be from the family of millions, and so forth. So it's easy because this is giving us an idea of an abacus. And with this, we can check on the right-hand side how many beads are there. 1, 2, 3. So that represents 3 ones. The next column or string will have 4 beads in it. So that's 4 tens. So those 2 columns tells us it's 43. If we add the third column, which will be hundreds, we have 1, 2. So it's 243. And now we move into thousands. So we have 6 of those, 6 ones, no tens, and 3 hundreds. So we have 306, 306,243. So let's go on now to number 2. In this question, they're asking us to look at which of the following numbers is the largest one and circle it. Now, when the question was given for the exam, it was written going across 101011, comma, 101110, comma, going straight across. Students may have gotten some problems with this, so I'm writing it downwards so we could sort of see a way of identifying which number is larger than the other. So still bringing up an idea of a place value chart because you're so accustomed to this, and this is the basics of number theory. So we have ones and tens and hundreds, and ones and tens and hundreds again. And just as we did in number one, the first set were for ones and the next set for thousands. So if we think about it, we have 1, 2, 3, 4, 5, 6 digits, and each of our numbers has 6 digits. So we can start on either side. I will start on the left-hand side. In the first number, there is a 1 there. So we can bring up a 1. That tells us it has 100,000. We can go across or we can go down, however you want to handle it. I will move down. In the second number, we also have 1 in the 6th place. So it's also 100,000. And in the third number, you can see a 1 as well. And in the fourth number, there's also a 1. Now, if we look at our question, it's asking us to circle the largest number below. Now, all 4 numbers carried 100,000. So we could not tell from that information which is the largest. Let's go to the next place. And in the next place, if we start at the number on top, that's 0. So we don't put anything. And if we come to the number below, it's also 0. And the third number is also 0. And the fourth number is also 0. So there are no 10,000s in any of the numbers. Right? So let's go now to the next digit. So that digit tells us in the first number, we have 101. So we have 1 going into that place value column, telling us that it's 101,000 for the first number. Let's look at the second number. There's 1, 0, and there's a 1 as well. So I'm bringing it up as these so you can visually see the actual values of them. And sometimes it's easier for students who are getting problems to be able to recognize and count, well, I have 2 green ones, well, it means 200,000, or 1 green one, 100,000. In the third number, it means that we have 101. And in the fourth number, do we have thousands? Yes, we do. So all 4 numbers have 101,000. So now we go to the next digit, which is hundreds. In the first number, 101, there's a 0 there, so we won't see anything. Let's look at the second digit. What is there? 101. And then what hundreds is there? There's 100 there. So we have identified that all 4 have 101,000. And we're going to bring up that 100 to identify this. And clearly we can see the second number is larger than the first number. The first number did not have any hundreds. So we'll already be able to give a direction to where the largest number is going to be. Let's look at the third number. The third number, when we look at the values there are no hundreds either. So the second number is larger than the first and the third. And let's look at the fourth number. The fourth number, there is a 1. So easily we can tell, because of the value that there's 100 in both the second and fourth numbers, that the first number could not be the largest number there. Any others? And the third number also, all 4 numbers have 101,000. But when we go to hundreds, the third number has no hundreds. So that cannot be the largest number. We're only looking at the largest number to circle. So we've now come on to tens. If we look at our second number there's 110 there. And there are no zeros, so I can't put any ones. And if we go into the fourth number, there are no tens. There's 0 tens, but there's 1 1. So which of these is larger? 110 or 101? Clearly 110. So that is our largest number. Let's move on to number 3 now, where in this question, they're giving us a number line. And on the number line, there are these numbers which are represented. 3,575, 3,650, 3,725. We don't know what number there is, and then 3,875. So this question is asking us, insert the missing number in the box. So we have to figure that out. So this should be going along up some sort of pattern. So if we look at this, and we look from left to right, you realize 3,575, 3,600 is getting larger. So if we move from left to right, it means we're going to get a little bigger. How much larger we're going to get? Can we tell that? We move from 3,575 until 3,650. So what is the difference? How do we find difference? We take the larger number, 3,650, minus the smaller number. And if we do that, let's look at the ones column. We have no ones up on top, but we want to take out or subtract 5 ones from it. Is that possible? No, it's not possible. So what teachers normally use the word borrow. We're actually regrouping, but that's fine. So we want to borrow from the tens. So we could go and cross out the 5, right? And we take out one of those tens. We're left with 4 tens there. And we have 1 10, and we're carrying it across to the ones. So how many ones will that be? That will be 10 ones. So we have 10 and 0 is 10. We now have 10 ones, and we want to take out 5 ones from there. So we're left with 5. Hopefully it makes sense. Let's go to the next column. We have 4 tens, and we want to take out 7 tens from that. Not possible. So we need to borrow or take from, or regroup from the 6, and that is 6 hundreds. So if we take out 100 from there, we'll be left with 5 hundreds. And we're taking that 100 and carrying it across. How many tens will that 100 give us? It will give us 10 tens. So we have 10 tens and 4 tens. It's 14 tens. And from 14 of those tens, we want to take out 7 of those tens. So we're left with 14 minus 7 is 7. Remember, 7 and 7 is 14. And now we're left with 3 and 5. We have 500s minus 500s is 0. We have 3,000 minus 3,000 is 0. Therefore, what is the difference between the first number and the second number? 75. So if we had 3,575 and we add 75 to it, we're going to end up at 3,650. That's what we did. Now, how do we move from 3,650 to the next number? What is that? Is it getting bigger? Yes, it is. So how much bigger? We need to find the difference. So let's go do that again. How do we find the difference? We put the larger number, 3,725, minus 3,650. And we subtract. Let's look at the ones. On the right-hand side, we have 5 ones minus 0. We're not taking anything from it, so we're left with 5. And now if you look in the second column, we have 2 tens on top, and we want to subtract 5 tens from it. Is that possible? No, it's not. So what do? We need to borrow from the hundreds. So we borrow from 700s, and we take one of those, we're left with 600s. And when we carry that 100 across, how many tens are we going to have? We're going to have 10 tens. So 10 tens and 2 tens are 12 tens. We now have 12 tens. You can use your fingers if you wish. And we're going to take away 5 of those tens from there. right? So we're left with 7 tens. And then we have 600s minus 600s, that's 0. 3,000 minus 3,000 is 0. What does this tell us? It tells us the difference between the second number and the third number is also 75. So as look at the pattern on the number line. From the first number to the second number, we added 75. From the second number to the third number, we're adding 75. Therefore, if we're going from the third number to the fourth number, what should we be doing? We should be adding 75 as well. And that will give us our missing number. So we're starting at 3,725, and we have to add the 75 now. So let's go do that. 3,725 plus 75, right? And when we do that, we're going to add our ones, 5, and 5 is 10. So we can cross the 0. Notice I tried to put it below rather than on the side, so students can easily see it's lining up. And when we add the tens, we have 2 tens and 7 tens. That's how many? 9 tens. And don't forget, look down below, we have one more 10. So 9 tens and 1 10 gives us 10 tens. So we cross the 0, as we were taught so many times in class. And we let those 10 tens gives us 100. We have 100, and up above we have 700s. So 700s and 100 is 800, and we have just 3,000. So that tells us we have 3,800 goes into the box. And the question is finished. But if you wanted to check, if we added following the pattern, what should we add to 3,800? Every time we go to the right, we should be adding 75. 3,800 plus 75 is 3,875. So the pattern makes sense. Great. Let's go on now to number 4. When we're looking at number 4, they're asking us to complete the number sentence below. 20 times something is equal to 20 times 3 and 20 times 4. So when I see these questions, there's so many different ways you can do it, right? I think of it as 20 times 3 sounds to me like length times breadth. It sort of looks like an area question. So if I have 20 rows of 3, let's bring that up. So we know 20 rows of 3 there. And next to it, what we have? 20 rows of 4. So hopefully we could see we putting them together. Then let's put the whole thing there. See it just as if it's an area question. It's the same thing as having 20 rows there of 7. 3 and 4 is 7. And that's it. Question is finished. If you would like different ways to do it, and let's just make sure we get a better understanding. What did we do? It's just like saying we had 2 sets of 5 and 2 sets of 3. Well, 2 5s are 10, 2 3s are 6, and 10 and 6s, 16. How do you get 16? 2 sets of 8. So if we look at that line there that's written in black, 2 times 5 and 2 times 3 is ending up to be 2 times 8. How are they getting 8? They're adding the 5 and the 3. And that's the same thing we did above. 20 sets of 3s and 20 sets of 4s. We added the 3 and 4, and we got 7. 20 sets of 7. Some people prefer to see it this way. We have 1 set of 3, 2 sets of 3s, and if we count in 3s going down, we want to look at the 20 sets of 3s. We just want to make sure students are clear on how this is, right? What's happening? 5 sets of 3s, and I put another 5, that's 10 sets of 3s, 15 sets of 3s, 20 sets of 3s. That represents, in the yellow balls, what the 20 sets of 3s are. Can we look at the 4s? Because 20 sets of 3s gives us 60. And if we look at the 4s now, we have 1 set of 4, 2 sets of 4s, 3 sets of 4s, 4 sets of 4s, 5 sets of 4s, another 5, that's 10 sets of 4s, 15 sets of 4s, 20 sets of 4s. So we have 20 sets of 3s, 20 sets of 4s. And if we group them straight across, remember 20 sets of 4s are 80, 60 and 80, 6 and 8 is 14, is 140. So that is just like telling us that we have a group. One group of 3 and 4 is 7. And how many do we have in all? 20 sets of 7. Which works out to be 7 twos are 14, 140. The same thing as 60 plus 80, 140. Okay, let's go. Let's move on now to looking at the idea of number 5. And in number 5, they're giving us a simple multiplication. Calculate 25 times 48. And for some students, it's straightforward, and others, they tend to make little mistakes hurrying. So I want to look at it a little differently from what you're accustomed doing with your teacher, right? So if you're getting problems that way, let's see if we could look at it a different way. Let's think of it as a rectangle. I'm thinking of it still like area. And one side is 25, and the other side is 48. Length times breadth, 25 times 48 will give us the whole thing. Now, 25 might be large. Can we break up 25? Let's put a line through there. We could break up 25 into 20 and 5. 20 and 5 is 25. What about the 48? Can we break that up into 10s and 1s? Well, how many 10s do we have? We have 4 10s. So we could say that's 40 and 8 1s. So 40 and 8, 48. So different ways of saying it. So let's look at that little rectangle up on top. The first one. Let me highlight it here. And in that teal color, if we have one side is 20 and one side is 40, what's the area? 4 2s are 8. We have 2 zeros, so that's 800. And what about below? Oh, sorry, to the right. Let's look at the yellow one. We had, that's not 25, that's 20 by 8. 8 2s are 16, and we have a 0. So 160, 160. Let's look at the one in brown. What are the dimensions of that? If we're finding the area of each part, length times breadth. Many teachers do it this way. Right? Then 5 4s are 20, and we add a 0. So it's 200, 200. And the last rectangle, we have 5 times 8, the length times breadth, which is 40. So what is the area of the whole thing? Well, we could add it up. 800 plus 200 plus 160. Anything else? 1, 2, 3, 4 of them. Plus 40. So we're going to add that. Then let's add the ones values. So everything is 0. So that'll give us a 0. 6 and 4, we add the 10's value is 10. So we could cross that out and put a 0 there. And let's count the hundreds. 800 and 200 is 10 hundreds, 11 hundreds, and 1 down below. That's 12 hundreds. So we could cross that, cross the 2 and put 200s here. And what we left with? 1,000. So our answer is what? 1,200. So we did this without really having to go through your normal steps one by one or your algorithm. But let's look at your algorithm. Some people put 25 times 48 or the other way around. It doesn't really matter. At this point, you can multiply by the 8 first. Some teachers teach that. Some students prefer multiplying by the 4 first. If we're putting the 4 first, and remember there's going to be a 0 because the 4 is 4 tens. So what is 4 25s? 4 25s are 100, and we have a 0 there. So if we think about it here, look on the left-hand side, that is 40 times 25. So I just highlighted it there. Let me rewind it so you could see it. Look on the left-hand side. 40 times 25 is that whole piece on the left side. And that is 800 and 200, which is 1,000. And we just said that 4 25s are 100, and we add a 0. So that's the whole left side. And what about 8 times 25? 8 times 25 would be the whole right side. Let's put that in purple. So 8 25s, right? If you know your 25 cents, you could count it 25 cents, 50 cents, 75 cents, 100. 125, 150, 175, 200. So that's 200, 8 by 25. And where did we get that 200 from? From the 160 and the 40. So now we could just add it up. What is 1,000 plus 200? Well, 0 and 0 tens and 200s and 1. So we're still getting 1,200. So there's so many different ways to do it. And some people find it's even easier when they're dealing with 25. They know 25 times 48, and they know a shortcut that 25 is really a piece of 100. What fraction of 100 is 25? 25 is a quarter of 100. So they could say, instead of writing 25, they could say 100 over 4. Because 4 into 100 is 25 times the same 48. And now they say, well, 4 into 4 is 1. And what is 4 into 48? 4 into 4. 4 is 1. 4 into 8 is 2. So it's 12. 4 into 48 is 12. And 12 hundreds are 1200. Let's now move on to number 6, where we're still on the strand of number. And it says that Ziad has a total of $15.10 in bills and coins. The value of one of the coins below is not shown. What is the value of the coin that is not shown? So we can easily see how many dollar bills there are, how many cents there are. There are 3 coins shown and 1 is missing. So we know the total is $15.10. Let's see if we can add up all the dollar bills first of all. So we have $10, and we add 1 more, that's 11, and 1 12, and 1 13, and 1 14. So that means we have $14 bills. And how much value do we have in coins? We have 50 cents, and another 25 cents, that's 75 cents, and another 10 cents carries us to 85 cents. So that means we have $14.85 so far. And we're missing 1 coin. And we know our total is $15.10. So what is the difference? For us to find the difference, we know the total is $15.10 minus $14.85. So now we do a simple subtraction. We have 0 cents on top, and we'd like to minus 5. We can't do that yet, so we need to borrow 1 of the 10 cents. And if we regroup that, we wouldn't have any more 10 cents anymore. That will be how many 1 cents? That will be 10 1 cents. So we have 10 and 0, which is 10 1 cents, and we're minusing 5 of those 1 cents from there. So we're left with 5. Now let's look at the 10 cent pieces. We have no 10 cent pieces, 0, but we would like to subtract 8 of those. How do we do that? We need to regroup or borrow. So we're borrowing from the dollars. We had 5 $1 bills, and we're going to borrow. So we're left with 4. So that $1 bill becomes how many 10 cent pieces? 10 10 cent pieces makes a dollar. So that means we have 10 and 0, which is 10 10 cent pieces, minus 8 10 cent pieces will be 2 10 cent pieces. And of course, we have a decimal point. And if we look at what we have on top, 14 minus 14, that's 0. So that indicates that what is missing is 25-cent piece. So that if we include that 25-cent piece, we can easily see that this gives us 15.10. Let's double check it. We had $14 bills, and let's count the cents now, 50 cents, and 25 cents is 75 cents. And let's add the other 25 cents. That will give us 50 and 25, 75, and 25 cents gives us another dollar. So $14 and $1 is $15 and 10 cents. Right? So it works. Let's move on to number 7. In that question, they're going to ask us what number must be placed in the box to make the number statement true. So we have the box. We have 27 over 45 is equal to 3 over what number? There are many different ways to work this out. Let's look at it visually first of all, so we can get some help. Let's put up the whole as one big rectangle, and let's cut it up into parts. There are different ways we can do this. So I'm going to draw some lines across. 1, 2, 3 pieces, 4 pieces, and on top will be 5 pieces. So what did we do? We took the whole and we cut it up into 5 parts. So each of those parts will be 1 out of 5, 1/5, 2/5, 3/5, and so forth, 4/5. And now let's go the other direction. Let's draw lines coming down. So we have 1 part, 2 parts, 3 parts, because we're aiming to get how many parts in all? 45 parts. So we had 5 on one side, and we're going 6, 7, 8, and the last piece will be 9. So what does that mean? We had 5 rows and 9 columns. 9 fives are 45. So we're no longer dealing with 5 parts of the whole, we're dealing with 45 parts of the whole. So the question was 27 out of 45. So is it the entire thing? The entire thing would be 45 parts. It's just 27 of those. So let's see if we could count them. We could count 1, 2, 3, and another 3 is 6, and 3 threes are 9, 4 threes are 12, 5 threes are 15, and another 3 is 18, 21, 24, 27. So what we have shaded is 27 parts out of 45. So if we look at our question, what number must be placed in the box to make the number statement true? On the left-hand side is 27 out of 45. And they're asking us 27 out of 45 is the same as 3 out of what? So if we consider one row going across as 1 part, and another row as 2 parts, and another row as 3 parts, well, that tells us something. It's 3 parts if we're counting rows only. Let's remove some of those lines so you can see it. And how many parts do we have in all now? The same shaded area which was in blue is now been highlighted and showing us 3 parts out of, not 45 anymore, out of 5. So it's 3 parts out of 5, or 3/5. So it's trying to show you a little visual explanation of how this reduction takes place. The typical way teachers teach it, 27 over 45 is equal to 3 over something. And how do we move from 27 to 3? Are we getting larger or smaller? From 27, we're getting smaller to go to 3. So does that mean we have to multiply by a number or divide? In order to get smaller, we divide by a whole number. So 27 divided by 9 is 3. So if we do that on top, and we do the same thing below, 45 divided by 9, and the answer is 5. So the number that needs to be placed in the box is 5. Or we could say it differently, 27 parts out of 45 parts, it's the same as 3 parts out of 5. Right, let's move on now to number 8, where in that question, we're going to be looking at a rectangle A, B, C, D below, which represents a hole. So this is an entire hole here, this large rectangle. And they're asking us to find what fraction of the rectangle is shaded. So we need to know the remainder. And there are many different ways to do this. Right? We can do addition and subtraction. We can do LCM, many different parts. So I'm going to try a different way. If we look at the first rectangle, we have 16 A, B, C, D. So we have 2, 4, 6, 8. We're going to cut up this 10, 11, 12, and 2 more, 14, and 2, 16. So it is the rectangle above was represented up to 16ths. So we're drawing 16 circles to represent the whole. And in this first part, that is 7/16. So we had 16 yellow circles. Let's consider that to be the whole. So if we want 7 of those, we'll have 1, 2, 3, 4, 5, 6, 7. So this first 7 represents the same thing as 7/16. Now what about the next part? The next part is 3/8. Now if we look at those 16 circular balls that we have, then can we cut that into 8 parts? Well, we could draw lines 1, 2, 3, 4, 5 parts, 6 parts, 7, 8 parts. So we have 8 columns, right, representing, that's how we divided the whole, and we want to get 3 of those columns. So let's look on the right-hand side. Let's take those 3 at the end. So 3 out of those 8 columns will represent 3 eighths. 1 8, 2 eighths, 3 eighths. So the first rectangle we had, 7/16, we represented with the 7 green balls. And the 3 eighths we represent with 3 of the 6 of those. Because 3 eighths, it's the same thing as 6 out of 16. And now we have 7/16 and 6/16, or 7 circles and 6 circles. So in all, from those 2 rectangles that we have 7 and 6, 13 circles. So what is the shaded part? What's the remainder? 3 yellow circles. We can count them easily. 1, 2, 3. 3 out of, what was the total? 3 out of 16. So this is a different way of approaching the question. I'm sure your teachers would have done this, right? Showing you many different parts, not just LCM alone. Let's move on now to number 9. In number 9, the question is asking us, John bought 340 seedlings. He planted 45% of the seedlings. How many seedlings did John plant? And there's so many ways to do this. I'll use a number line, 0%, 10%, 20%, 30%. Remember, he planted how many? 45%. So 40%, 50%, even 100% going up. So if we picture drawing a number line, we're 0 to 100%. And that means that 0% is 0 here. And remember that we want to find 45%. So that's halfway between 40 and 50. So 0% is 0 seedlings, and 100%, that's all the seedlings, 340. So if 100% is 340, can we cut that into 10 parts? Well, 1/10, or we cut 100% into 10 parts, then we have 10%. And we cut 340 into 10, then the zeros will cancel, we're left with 34. So that means 10% is 34. And if we add another 10% to carry us to 20%, that's another 34. And we want another 10% because we want to go from 20 to 30. That's another 34. And from 30 to 40, that's another 34. And from 40, are we going to 50? If we're going 40 to 50, that's 34. But where are we meeting? We're meeting at 45, which is halfway. So we only need half of 34. Half of 34 is 17. So that tells us how many seedlings we need to show that John planted 45% of those. So let's add them up. 34 seedlings and another 34 and another 34. How many 34s are there? 1, 2, 3, 4 34s and 17. And let's do some addition. 4 4s are 16. 16 and 7 is 23. So we can cross out the 3 as teachers do, and you write the 3 under the 1s column. And let's look at the next column. We have 3 and 3 6 and 3 9 and 3 12 and 1 13. And don't forget there's 2 more down below. So that will mean that's 15. 5 and a 1. So we finished. John planted 45% of the seedlings, which is 153 seedlings. I'll just show you another diagram you could have used, and you do the same working. If we consider the rectangle as the whole as 100%, and we cut it into 10 parts, let's do that. If we notice 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns, right? We're cutting into 10 parts. Each part is 10%. So this first part will be 10%, which represents 10% of 340, that's 34. And another 10% to make it 20%, that's another 34. And another 10%, that makes it 30%. So that's 3 34s. And another 10% to make it 40%. So that's 4 34s. And do we want to get another 10% to make it 50%? No, we want to get half of that. So we could draw a line going across. So it's not 34 anymore, but it's 17. So it gives the same working as what we did on the left-hand side, just using a different diagram. One of the things we want for you to get a better grasp of the math is to try and represent the questions with diagrams. So we had 4 34s and a 17, which is the working on the left-hand side, which will still give us 153. Of course, we could do the standard working, where teachers tell us 45% of 340. How do we write that? 45%. Percent means per means out of a cent or a century, out of 100. So we can rewrite that 45 out of 100 multiplied by 340. And of course, we can reduce here. We can say 10 into 100 is 10, and 10 into 340 is 34. Let's see what else can be reduced. Look, some of these things looking like they're on our 5 times table. So we could say 5 into 45, and that will give us 9. And 5 into 10 will give us 2. And finally, 2 is an even number. 9 is not an even number, but 34 is. It ends with 4. So we have 2 and 34 are even numbers. That means they are both divisible by 2. So 2 into 2 is 1. 2 into 34 is 17. Now, if we think of that diagram, any one of those that we did before, let's look at the one in the center of the page. We had 34, 34, 34, 4 of those, and the 17. The 17 was a small square we're seeing there. If we count up how many small squares are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 small squares. And each of those squares is worth 17. That's why our working has now brought us to the point where we're trying to find out what is 9 times 17. And of course, 17 times 9, there are many different ways to do this as well. Some people will say 17 times 10 minus 17. Right, so 17 times 9, 9 sevens are 63. And we can cross the 3 and write it under the ones column. And 9 ones are 9. And 9, and there's a 6 below. So 9 and 6 is 15. 5 and 1, 153. So we still get the same answer. Hopefully we can see why we're multiplying 9 by 17. So let's go on now to the last question in the number strand, which is number 10. Some students are ordering numbered blocks. So the blocks have numbers on them. The diagram below shows how 4 students ordered their blocks. So when they received their blocks, Anne, Bob, Carl, and Dan, they placed it in this order: 5.03, 5.3, 5.38, and 5.4. So they chose a special order to put it in. Faye chooses the block shown below. And we'll bring it up in a different color so you can clearly see the difference. Faye chose 5.13. So the question is asking, between which two students' blocks should Faye place her block? Should. So clearly it means if it's fitting between two blocks, it cannot be in front of Anne and it cannot be after Dan. It will either be between Anne and Bob, or between Bob and Carl, or between Carl and Dan. So we need to figure out where does it fit. Now, one of the things to remember here is if we identify 5.03 as Anne's, right? Sometimes some students get confused when there's one decimal point, or one decimal place, and two decimal places. So let's write all of them as if there were two decimal places, and that may help us. So Anne is 5.03, Bob is 5.3, and if we write that to two decimal places, it will be 5.30. And Carl is already to two decimal places, 5.38. And what about Dan at 5.4? Can be written as two decimal places as 5.40. Right? It's just to make sure we don't write 5.04. Good. Now that we have this, can we see an order? Well, let's put a number line showing from 5.0, 5.10, 5.20, 5.30, 5.40, and so forth. Now, where will Anne fit? Anne is not at 5.00, it's at just a little above 5.03. So let's just put an idea that Anne fits somewhere here. Where does Bob fit? Bob is not 5.3. To confuse some, let's use the idea of 5.30. So that's Bob up there at the fourth brown marker. So we have Anne, and then we have Bob. We're trying to see the pattern that these students decided in order to order their blocks. What about Carl? Carl is at 5.38. So Carl is above Bob. So Anne was down below, and then Bob is higher, and Carl is even further up. What about Dan? Dan is at 5.40. So he's at the highest point. So they ordered it, Anne, and then Bob, and then Carl, and then Dan, which means that they were ordering it, if we're going from left to right, from smallest to largest. Or we can see they ordered it in ascending order. So if that's the case, where does Faye fit? So Faye is at 5.13. It's already at two decimal places, so you can see it easily, which means Faye fits where? Between 5.0 and 5.10? Or between 5.10 and 5.20? Yes, that's where she fits. So Faye fits there, which means that if we were writing the order, how would we put it? What would be the first block? The first one will be Anne at 5.03. And what comes after Anne? Faye at 5.13. And then Bob at 5.30 or 5.3 as written on the block. And then Carl at 5.38. Who comes next? Dan at 5.4. So this shows understanding of number and values and place values. So let's look at the question, between which students' blocks should Faye place her block? She should place it between Anne and Bob because her block is more than Anne's but less than Bob's. So that brings us to the end of number, and let's go on to number 11, where we now move into a new strand. So the calendar represents the month of June. So we've moved into the topic in that strand of time. Jade visited the dentist on the 8th of June and has to return exactly 2 weeks later. So let's identify the 8th of June. And if we want to return exactly 2 weeks later, on what date should Jane return? So look, it's a Monday that she went on the 8th of June, and she wants to come back 2 weeks later. 1 week later will mean that she's going on the 15th. And the second week, exactly 2 weeks later, will be another Monday, which will be the 22nd of June. So it's still Monday. Monday, the 22nd of June will be our answer. Or we can do some working. We started on the 8th of June, and it's exactly 2 weeks later, which means we're adding what number? We're adding the number 14. 7 and 7 is 14. That's 2 weeks. And if we do some addition here, 8 and 4, that's 12. So we can cross the 2 and put it there under the 1's column. And look under the 10's column. We have 1 and 1 below. So 1 and 1 is 2. So it still gives us the 22nd of June. Let's now move on to number 12. And in this question, where we're looking at the idea of the perimeter of the pentagon A, B, C, D, E is shown below. And it has a perimeter of 148 centimeters. So if we remember perimeter, means a measure of distance, and peri means part of the word periphery, which means going around. So it's a distance around the object. So if we look at that, the distance around the object, how many sides does this object have? Let's count it. A to B, that's 1. B to C, that's 2. C to D, 3. D to E, 4. E to A, 5. They have 5 sides. And if we get that total distance, it is 148 centimeters. Did they give us all 5 sides? Let's see what's in green. 16, 40, 40, and 22. So they give us 4 of the sides. So what do you think the question is? What is the length of BC? Meaning we are missing that length in order to get our whole perimeter as 148 centimeters. So BC is missing. But if we added BC and this 22 centimeters and this 40 centimeters and this 40 centimeters and that's 16 centimeters, that whole distance would be 148 centimeters. So one of the things that would have done when your teacher was showing you perimeter is, how do we find the perimeter of our waist? We could take a string, put it around our waist for it to touch, and then open back the string out to get a straight line, and then check the distance. So let's see if we could do that. Let's look at CD. Can we now turn that so that it becomes a straight line? So that is still 22 centimeters long, and it's still the distance from D to C. What about the other red parts? Well, we could turn that to the left because we want to get a straight line. So that means E to A is 40 centimeters. Oh, and we have that extra piece still sticking out. Let's turn that as well. So that will be A to B, which is 16 centimeters. So the red parts, we know the lengths of 1, 2, 3, 4 sides. And the only thing missing is BC. So can we figure out that length? Well, we can add it up. 16 centimeters for AB and 40 centimeters for AE. 40 centimeters again and of course 22 centimeters. So when we add those four sides, let's add them up. 6 and 2 is 8. And let's see, 4 and 4 is 8, and 2 is 10, and 1 is 11. So you can cross it and put that there. We're going to get 1 there and 1. So that means the four sides, which were in red, those four sides adds up to 118 centimeters. Now the whole thing, the whole perimeter of that entire pentagon, that five-sided shape, that's what pentagon is, 5 sides, is 148 centimeters. And we know 4 of those sides. So what's the difference between the five-sided shape and the ones we have? It is the distance of BC. That is what is missing. So how do we find difference? We know the whole thing, which is 148. And to find difference, we take away from the 4 of those sides that we know, 118. And let's do some subtraction. 8 minus 8, that's 0. 4 minus 1 is 3. And 1 minus 1 is 0. So there's 30. So it means that the length of BC is 30 centimeters. And if we put it back in there and add all 5, it will give us the perimeter, which is written up on top as 148 centimeters. So let's go again. Let's look at number 13. As we move to number 13, this is a question looking at mass. So the diagram below shows a fish on a scale. And if we know that, state the mass of the fish in kilograms. So it's one fish alone, and it gives us a reading. So let's draw a line going across a little bigger so you could see it. It's exactly the middle of 1 kilogram and 2 kilograms. And what's the middle of those? 1.5 kilograms. Let's now go on to number 14. In this question here, Paul pours 3 liters of water into a number of 250 ml cups. So we have 3 liters in this large jug, and we have these small cups of 250 milliliters. How many cups can be filled completely? So if we recall, 1 liter is how many milliliters? Because we have liters and milliliters. 1 liter is 1,000 milliliters. So if we try to represent that, let's use it as a straight cylinder. 1 liter is that first cylinder, 1,000 milliliters. And we have 2 liters, so that's another 1,000. And if you look at the jug, it's 3 liters, so that's another 1,000 milliliters. And let's try and see, we want to know how many cups we can get out of this. If each cup holds how much? 250 ml. So if we put 1 cup, it will reach 250. If we fill a second cup, 250 and 250 is 500 ml. If we fill a third cup, it will give us another 250, which is 750 ml. If we add a fourth cup, then that will give us 1,000 milliliters. So 4 cups can be filled from 1,000 milliliters of water, or 1 liter of water. So let's bring that up. So what happens to the next 1,000 milliliters? How many cups will that give us? Following the same thing, 1, 2, 3, 4. So 4 cups again from the second 1 liter. And for the third 1 liter, it will follow the same pattern. 1 cup, 2 cups, 3 cups, 4 cups. So how many cups are there in all? 4 and 4, 8, and 4, 12 cups. So 12 cups can be completely filled at 250 milliliters by a 3-liter jug. Is there another way to do this? Well, we could think of it this way. Many teachers will encourage you to go and do some division. How many 250 mLs can we get in 3 liters? And that's fine, except they are two different units. So we can either change the 3 liters to 3,000 liters and say 3,000 divided by 250. We're working in milliliters both, or we can just work in liters. So we have 3 liters, and how many of those? What is a cup? How many cups made a liter? 1, 2, 3, 4. So 1 cup was a quarter liter. So how many quarter liters cups can we get from 3 liters? So we could say 3 divided by a quarter. And if you remember your rules, that when we're dividing by a quarter, it's the same thing as if we're multiplying by its reciprocal, by its inverse, by flipping it over. So 3 multiplied by 4/1, and 3 fours are 12 cups. Because each liter gave us 4 quarters, and we had 3 liters, so 3 fours are 12. All right, let's move on to number 15. So in this question here, number 15, we're saying that the solids A, B, C, and D are shown below. So A looks like a rectangular base pyramid. B is a triangular base pyramid or tetrahedron. C will be coming to a point. It will be a cone. And D, let's see, is that coming to a point? No, it's not. So that's the only one that's not a pyramid. It's a prism. So which solid has a uniform cross-section in the shape of a triangle? So let's draw this a little bigger. And if we have the base, that's a big rectangle, and we come halfway up, we're going to get another rectangle, but a little smaller. And if we keep coming higher, we're going to get another rectangle, which is even smaller. So the cross-section, if we cut it, is going to maintain the same shape, the same rectangle, except the size will be changing. So it's not the same size. As such, for this first diagram, it is not uniform, not the same. Let's try for the triangular base pyramid. So we have a triangle at the base, a large triangle. And if we come up a little bit, we'll get a triangle again, but a smaller one. And if we come up even further, we're going to get another triangle, except even smaller. So the cross-section maintains the shape, but the size changes. It is not constant. It is not uniform. Let's try the cone. And at the cone, what shape you're going to get at the base? Right? You're going to get a circle. We have our axis here so you can see. I'm going to get a smaller circle as we come up, and even a smaller circle. So all 3 of them are following the same ideas, that the shape remains the same, but it's getting smaller and smaller as it heads towards the top. Right? So clearly A is not the answer. It's not uniform. B is not the answer. It's not uniform. C is not the answer. So D must be the answer. Or we can draw that over a little bigger so you can see it. And what is the shape at the back? A triangle. What is the shape at the front? A triangle of the same size. What's the shape halfway through? Another triangle. So all through, the same shape remains and the same size. So it's a uniform cross-section. So D is clearly the answer. Let's move on. Number 16. The first 4 elements of a pattern are shown below. Complete the 5th pattern. So we have the first pattern. Let's take a look at it. It looks kind of like a bicycle tire, where it has 8 spokes. So it cuts the circle into 8 parts. And then the second element, same thing. All 5 elements, same basic circle, cut into 8 parts. But what's the difference between the first and the second? The shaded part has moved. And then it's moved again in the 3rd element. And it's moved again in the 4th element. So where will it end up in the fifth element? So let's redraw that first one. Let's bring up this circle with the 8 parts and show the part which is shaded. And now let's redraw that here and figure out how did the first element move and become the second element? Well, maybe it turned. So it turned 1, 2 parts, 3 parts, 4 parts, 5 parts. So it moved 5 parts in a clockwise direction. That's how it moved from the first element to the second element. Let's take the second element now. How does the second element become the third? Well, will it turn again in a clockwise direction? Let's see how many. 1, 2, 3, 4, 5. So to move from the first to the second element, it turned clockwise 5 parts, or 5 out of 8. 5/8 of a circle. To go from the second element to the third element, it moved 5 parts out of 8 again in a clockwise direction. Will it do the same thing for the fourth element? So let's start from the third element and let's see how it moves. 1, 2, 3, 4, 5. And yes, it ends up looking like the fourth element. So as it moves from one element to the other, it's turning clockwise 5 parts. Or it could have turned in the opposite direction, anti-clockwise. How many parts? 3 parts. And now we want to find the fifth element because we're finding the fifth pattern. So let's draw back the fourth pattern. And now it's moving clockwise again. 1, 2, 3, 4, 5. So this tells us that if we shade it above, that's the fifth element. And we can clearly see it's maintaining that turn of 5 fractions or 5/8 turn in the clockwise direction. Or you could have done it the other way, 3/8 turn in the anti-clockwise direction. Right, let's go on to number 17. So this is the last one in this strand, where they're telling us to draw all the lines of symmetry of the figure below. And what figure we have? A figure 8. So remember, a line of symmetry means an imaginary line that we have passing through the object, that it would be a place where we can fold the object equally so that the two halves will fit exactly one over the other. So if we look at this, can I draw a line coming down through the center? And let's see. If I shade that one side and I turn it, it gets the other side. Therefore, that's the line of symmetry coming down. Do we have any more lines of symmetry? Well, maybe you could have going across. And if we shade it up as a purple circle, and then we turn it, look here, or fold it over, we could see another one. So it's above and below as well. So we got a line of symmetry going up and down vertically and one going across. So those are our lines of symmetry in this figure below. Let's go on to our last 3 questions, which is our last strand. We just did measurement and geometry. So our last strand is statistics. Number 18, students' scores on a quiz are shown below. 4, one child got 3, one got 2, another one got 5, 1, 0, 3, 2, 3, 1. And they're asking us, if we have these scores from these different students, what is the model score? So the model score, let's remember what mode means. M-O-D-E means M-O-S-T, most. Frequent. So which one of these numbers are we seeing the most? Let's shade the 0, the gray coloring. Do we have any more zeros to shade? No, we don't. We have one gray coloring. What about the yellows? Right, the yellow square to represent 1. Do we have any more? Oh yes, we have a second one at the end. So we have 2 squares. What about the number 2? We could shade it in green. So we have a green rectangle to bring up the number 2. Are there any more 2s? Let's look down. Oh, there's one close to the end. So there are 2 yellows. There are 2 greens. Those are the most so far. Only 1 gray. What about 3s? Well, let's bring them up in purple. We have 1 3. There's a second 3. There's a third 3. So there are 3 purples. That's the most of any color so far. How many 4s there are? There's 1 4. That's it. And there's 1 5. We don't have to shade that. That's the one remaining. So what is the modal score? Which one of these appeared the most? The number which is shaded by the purple rectangle, which is the number 3. So that's clearly obvious. Let's move on now to number 19. In that question, they're asking us the mean of a set of numbers is 22. The mean or the average, the sum of the set of numbers is 132. So we have numbers that are averaging 22. And when we put all of those numbers together, we get 132. How many numbers are there in this set? So there are so many different ways to work this. I, as usual, try to draw a diagram. So let's imagine this is our base. And we know the mean. The mean tells us our average means that if we had to count numbers, they would all basically end up at this level of 22. Some will be higher, some will be lower, but they will balance out at 22. And is it possible that all the numbers could be 22? Maybe, because if that's the case, it will still maintain that average. So let's work with that. If the first number is 22, then we have 22 as the total or the sum. If we add a second number, also being 22, then our sum will be 22 and 22, 44. If we have a third number, which is 22, 3 22, 3 2s are 6, 3 2s are 6, 66. Did that reach our sum as yet? So our sum is 66. It's increasing, but it hasn't reached where we wanted. Can we add a fourth number? Then that fourth number will bring us to a sum of 88. If we add a fifth 22, what happens? 88 and 2, 89, 90. 90 and 10 is 100, and another 10 is 110. So if we had it here, it's showing us that the mean of the set of numbers is 22, but the sum, if there were only 5 numbers, is 110 right now. We didn't reach our total, so let's add another 22. So that will give us 132. So it tells us that when we have 6 numbers averaging 22, then that total or the sum is 132. So there are 6 numbers in the set. Is there another way you could have done this? Of course. We could imagine we don't know how many 22s there are, but there are a certain amount of 22s which will eventually give us 132. Is it 122? Is it 4 22s? Is it 12 22s? So if we wanted to find that number in the box, then when we look at it again, it will be 132 divided by 22. Can we divide these? Well, let's see. Is 22 an even number? Yes, it is. So you could divide by 2. Is 132 an even number? Yes, it ends with 2. So we could divide by 2. So let's divide 2 into 22. That will give us 11. And 2 into 132. 2 into 13 is 6. 6 2s are 12. We have a remainder of 1. So that means 2 into 12. And that is 6. So we're left with 66 over 11. So this is another way of doing it. What could go into 11 and 66? Both of them are in the 11 times table. So we could use 11 into 11. And that will be 1. And 11 into 66. And that is 6. So 6 over 1, that's the same thing as 6. So it tells us that if we have 6 numbers, each being 22, 6 22s are 132, it will give us our sum. And moving on to our final question, number 20, to finish section 1. The block graph below shows the number of minutes 5 children spent playing. So Nicholas played for how long? We don't know. We don't know how many minutes, but it was 4 blocks. And Devika for 1 block and so forth. The children spent a total of 100 minutes playing in all. How many minutes did Keith spend playing? So we know Nicholas had 4 blocks of playing time. Devika had 1 block of playing time. What about Indira? 1, 2, 3, 4, 5 blocks of playing time. Lee had the most. We already have 5 there, 6, 7. So 7 blocks of playing time. And Keith had 1, 2, 3, 3 blocks of playing time. So in all, how many blocks are there? 4 and 1, 5. 5 and 5 is 10. 7 and 3 is 10. 10 and 10 is 20. So 20 blocks of playing time is 100 minutes, because the second line said that the children spent a total of 100 minutes playing. So 20 blocks of playing time was worth 100 minutes. So what is 1 block of playing time be? 100 divided by 20. And how many 20s can we get into 100? If we think of money, how many $20 bills are there to make 100? Well, it'll be 5. So 1 block represents 5 minutes of playing time. So Keith had 5 minutes for the first block, 5 minutes for the second block, and 5 minutes for the third block. As such, Keith had a total of 5 threes are 15 minutes of playing time. Or we could do some working like this. If 1 block of playing time is 5 minutes, 3 blocks of playing time is 3 times 5, which is 15 minutes. So this brings us now to the end of this SEA 2025 past paper question, specifically looking at section 1. When we started the series, we started with the year 2019. That was our first solution. And we have done each year up to this present year, which is 2025. Okay, you all take care. Hopefully you have gotten some benefit from this. Bye.